Okay, everybody, today's lesson is on acids and bases. This is an introductory video into what acids and bases are. Hopefully you've had some exposure to these in the past, hopefully in another class, maybe usually in 8th grade, 7th grade, freshman year. You sometimes talk about acids and bases, so you should have a general idea of the differences. But if not, here are some differences between acids and bases. So I'm expecting you to know some general properties of acids. One, they do taste sour, so that's where we get that sour flavor from, is from anything that's acidic. Lemons are very sour, so they're very acidic. They have the strong amounts of citric acid in them. Uh, they turn litmus paper red. So litmus paper is a way to test whether we have an acid or a base. So litmus paper test would be if it turns red, we have an acid. If we have litmus paper and it turns blue, then we have a base. Now, as I said before, acids taste sour, bases taste bitter. And this is where the name for acids come from, by the way. The acidus was the Latin word for sour. So people have known about acids and bases for a long time. And what they were doing was they were able to say, okay, if anything that has that acidus taste was classified as an acidus substance, which is what we call an acid. So it was really based on this taste in the beginning. Now, we're not going to use taste as our breakdown of whether we have an acid or a base, because I'm not going to be tasting things in the lab. So one we're going to do is a litmus paper test to determine if it's an acid or a base. Another way is to use something called pH, and I'll talk a little bit more about what pH is in the last video that we're going to talk, well, not the last one, but one of the videos we're going to talk about later, which is a way of measuring the relative range of acid and bases. Anyway, you should know that lower than 7 is an acid, higher than 7 is a base. We talked about this in one of the labs we did earlier. And at 7, we would say that the substance is neutral. All right. And the other thing that acids do is they neutralize bases. And a base is going to neutralize an acid. So we put these two together. When an acid and a base react together, they're going to neutralize each other. We talked about that back in the solutions chapter with the neutralization reactions between acids and bases. So like I said, we've talked about these before. You probably have some exposure to them at some point in the past. Okay? All right, so let's move on to acids, or a little bit more depth into what acids are. Now, as I said, people have known about acids and bases for a long time, but they had no way of really explaining where that acid property came from. Why was it that they tasted sour? Why did they turn litmus paper red? Why did they neutralize a base? Why was it that when I put these two together, they would take a sour tasting substance, you would add a bitter tasting substance, and it would then make it taste salty? Okay, the reason for that is that what we have is a definition, a working definition. This is by Savant Arrhenius, and here he is right here, Savant Arrhenius. He was the first one to come up with a working definition. He said that those acid properties were due to something called a hydrogen ion. So the hydrogen ion is put into solution. So we have something called hydrochloric acid, which we know is an acid. When we put it into water, it dissociates into ions, and it produces this hydrogen ion. It's that hydrogen ion that causes our solution to become acidic. So it's the hydrogen ion that's the cause of this. He said that the base was due to something called a hydroxide, and we've talked about hydroxides all year. You know about hydroxides. These are our bases. So our hydrogen ion contributes to the acid, and the hydroxide contributes to the base. Now, if I have a hydrogen ion and I react that with a hydroxide ion, and I have something that's an acidic flavor, it has a sour taste, makes litmus paper red. I have something that's bitter tasting and turns litmus paper blue. And I combine them together in the right ratio, what I will do is I will create water. We know this from the first semester when we did predicting products. It's the fact that this gets removed and this gets removed, and we have just water. Okay. Now, if I have a reaction between sodium hydroxide and hydrochloric acid, again, let's take a look at that. Sodium hydroxide and hydrochloric acid. Okay, what I'm going to do is I take these acids and this base and I react it together. I'm going to make water, HOH, so I get my water from the hydrogen and the hydroxide, and what I have left behind is sodium chloride. And this is why when we take an acid that tastes sour and mix it with something like a base that tastes bitter, we end up with salty water. Right? So it's going to taste like salt water. Now, this is only true if we truly neutralize. So you got to be careful here, because we're going to look at something called a titration a little bit later to see if these actually become neutralized. Because if they're not, if one of these is excess and left over, then I'm going to have an acid or a base still in solution. So we'll talk more about that when we get to those reactions. All right, now the problem with Savant's definition is that when we look at acids and bases, an acid has to have a hydrogen ion. A base has to have a hydroxide ion. Now let me show you something. Here's something called ammonia, NH3. Ammonia is bitter. Ammonia is going to turn litmus paper blue. Ammonia, if you were to measure its pH, would be higher than 7. So we would say that ammonia is considered a base. So this is considered a base. But wait a minute. There's no hydroxide in here. This is the problem with Arrhenius' definition. It's not that his definition is wrong. It's just that his definition isn't broad enough to cover something like ammonia. So there was a little bit of a problem with Savant's model or theory of acids and bases. So what we have to do is we have to expand our definition to encompass something like ammonia. So we have a new definition, and our new definition, this is the one we're going to use most often in this class. This is referred to as the Bronsted-Lowry acid-base definition. Okay, and this is the framework that we use for all of our acids and bases. The acid definition is pretty much the same idea, that it's focusing on the fact that we are creating hydrogen ions in solution. So we have hydrogen ions that are being created in solution, so the same idea. They say that the substance donates a hydrogen ion. I'm not really crazy about the idea of donating because nothing readily gives up the hydrogen ion. I'm going to show you what's actually happening here, why this is dissociating in just a little bit. The base is going to accept the hydrogen ion. So now what we can see is that when the ammonia, why is it considered a base? Because when it reacts with a water, okay, when I put ammonia into water, make it aqueous, the water is going to react with the ammonia. Now remember, I like to write this as HOH. Another reason I like to do this is because now I can see that the hydrogen ion is being attracted to the ammonia, and what happens is it creates NH4. So remember, it's the hydrogen ion that's moving from one side to another. So remember, it's a hydrogen ion that is moving from the water and going over here to ammonia. So that's why it has a positive charge, and we get an extra hydrogen on here. As a result, what's left over is that OH, and it has a negative charge. This is what makes it a base. Okay, so what we see here is that with the Bronsted-Lowry definition, we can now take something like ammonia that before we said didn't fit into Arrhenius' definition, and we can now put it into the Bronsted-Lowry definition of an acid and a base. So we can see that the base is really this reaction between the ammonia and the water. Now for the acid reaction, let me show you that one real quick. What's going on here really is that acid is really doing the same thing as the ammonia. It's really reacting with the water. Now it's doing something a little bit different. I'm going to keep water in this format here because what's happening is that this is an acid. So what should the acid do? It should donate the hydrogen ion. So it's going to give its whole hydrogen ion to the water. Remember, it's a hydrogen ion that it's giving, so it's going to make it H3O plus, and what it does is it leaves behind the Cl minus. And this is what makes our solution acidic. So this is going to make this an acid. Oops, can't really see that, but that would be, let's write it over here. This is what makes our solution an acid. Okay, it's the fact that the hydrogen ion is donating, in a sense. Really what's happening is the water is pulling the hydrogen ion into its structure. It's more the water pulling than the hydrogen, the chloride in this case, giving up the hydrogen ion. Same thing here. The ammonia is pulling the hydrogen ion from the water to make this reaction happen. Okay? All right, so we got our Bronsted-Lowry definition. That's the one that we're going to work with most often. So, as I said before, the hydrogen ion, this is the reaction I just showed you over there. This is going to create what's called a hydronium ion. This is referred to as a hydronium ion. So, acids are going to produce these hydrogen ions in water. And as a result of that, what we get is a hydronium ion in the water. So, we get hydronium. This is H3O plus, the hydronium ion. Okay. So, in an acid-base reaction, what's really happening is a transfer of hydrogen ions. You might hear me call this a proton because a hydrogen ion is really nothing more than a proton in the middle, right? Because it's what hydrogen has, one proton, and it has one electron, right? It has one electron. Well, if we're talking about the hydrogen ion, the electron is lost, and when that electron is lost, what you're left with is just a proton. So really, a hydrogen ion is nothing more than a proton. Okay, so I might talk about that and say that in class, so just something I tend to do. Anyways, the hydrogen ion in solution reacts to water to create the hydronium ion. So hydronium ion is really what's there. Now chemists tend to not write it that way. I'll show you that in just a second. But first, let me show you something else. So we have an acid-base reaction. It's something like HCl that I showed you earlier reacting with sodium hydroxide. This is considered the base because what's going to happen is the hydrogen ion is going to move. So we got our hydrogen ion here. Okay, so we got the hydrogen ion. It's going to move from here to here. Okay, it's going to replace that sodium ion. So as a product for this reaction, what I'm going to end up with is I'm going to have oops, that's okay, let's keep it this color, OH, because it now has the hydrogen ion. What I'm left with is sodium chloride. Okay, so this is considered my acid because it lost the hydrogen ion. This is considered the base because it gained the hydrogen ion. So really what this reaction is a transfer of hydrogen ions from one compound to the other. Okay. Now, as I was going to say before, is if we look at that acid reaction with water, what tends to happen when we react this with water is we get the hydronium ion, H3O+, and we look at the chloride ion being left out. Well, because water is on both sides, what chemists tend to do, and you're going to see me do this a lot, is we drop the water out. If I drop water out of this, what I'm left with is a hydrogen ion. So this is kind of a little shortcut way of writing acid-base reactions, is just writing them like this. So you're going to see this quite a bit. So the moral of the story, what I'm trying to get you to see is that wherever we have a hydrogen ion is equal to a hydronium ion. We just don't write it like this that often. We tend to just focus more on this because we don't want to add the water. Because water is a liquid and we start doing equilibrium with this, we don't want water in our equilibrium position at all. We want to get rid of it. Okay? So that would be our Bronsted-Lowry definition of it. Now, as a result of this, what happens with acids and bases is they always come together in groups or pairs, what are referred to as conjugate pairs. Okay? So a conjugate differs only by a hydrogen ion. So what happens is that when this reaction happens, when HCl loses a hydrogen ion, all right, what's happening is that the Cl- now has the ability to take a hydrogen ion. So this reaction could go backwards. So what's going to happen is that this can act as an acid, this will act as a base. So these two here, the acid and this, are connected together with each other as conjugate pairs. Okay, because if this loses a hydrogen ion, which is the acid, right, we would call this as an acid. We would say this is the acid. Oh, it keeps changing color again. Okay, this is the acid. This becomes the base, and it's a conjugate base pair. So let's take a look at this a little bit more closely with the examples that I have on the slide here. And we'll look at this more in class. I know these conjugate pairs and stuff can be a little confusing in the beginning. So if I take a look at this first reaction here, I'm going to take that ammonia minus. Now I'm going to rewrite the water as HOH. I like to write it this way because it makes it a little bit easier to see what's actually happening here. So let's rewrite that as HOH. All right, so the ammonia, the NH3, is acting as the base. Why? Because it's taking the hydrogen ion. The hydrogen ion is going from here over to here. How do I know that? Because I have ammonium over here. So if this is the base, this has to be the acid. Why? Because the definition of a Bronsted-Lowry acid is that it loses the hydrogen ion. Definition of the base is that it gains the hydrogen ion. Now let's take a look at this side. Because there's equilibrium here, I can think about the reaction going in the opposite direction. What's happening in that direction? Well, I'm going to take a hydrogen ion and go backwards and give it back to the hydroxide. So what I have here is I have the acid, and I could say that this is a base because, again, it's taking the hydrogen ion from the ammonium. So in any of these reactions, I always have this pattern of acid, base, or base, acid, and then acid, base. Not always going to follow that order. It could be reversed. But the idea is that on one side I have an acid and a base, and on the other side I have an acid and a base. Now these are going to go together in what are called conjugate pairs. So my conjugates are going to be the base going with the acid. So that is a conjugate pair. The ammonium differs by a hydrogen ion. They differ by one hydrogen ion. The water and the hydroxide are another conjugate pair because, again, they are the ones that are differing by a hydrogen ion. So we would say that these two are conjugate pairs. Okay? All right, we'll try it again. Do one more here. Okay, again, what we're going to do is we're going to look at coming up with the pairs. Now, this is the acid. Why is this the acid? Because it's going to lose the hydrogen ion to the ammonia. How do I know? Because look what's left over. Fluoride ions. Okay, so the hydrogen ion goes to the ammonia, therefore acid. What's happening is this is taking the hydrogen ion, therefore it's the base. Okay, those are my acid bases. Now over here, the fluoride is going to take a hydrogen ion to go back in this direction to create back the hydrofluoric acid. That makes this the base, and therefore this is the acid. So what are my conjugate pairs? Well, my conjugate pairs are going to be hydrofluoric and the fluoride ion. That's one conjugate pair. My second conjugate pair is the ammonia and the ammonium. Okay, we'll look at more of this in class. This is just an introduction, so just to get you started, and we'll take care of. I'll answer all your questions in class. See you later, guys.